All right, we're going to do the notes for 10.5 and talk about tangents. All right, so what is a tangent? A tangent is a line intersecting the edge or just one single point of a circle. All right, the point of tangency is that single point at which a tangent touches the circle. So in this image here, we've got circle C, so it's named by its center, and we have a tangent line AB that touches the circle at one point, point A, which we call the point of tangency. And then we have the tangent theorem. If a line is tangent to a circle, so line L is tangent to the circle with a point of tangency of T, then we are able to say that the tangent line is perpendicular to a radius of the circle. All right, and that radius is the one that connects the center of the circle to the point of tangency. All right, so let's go through some examples. Determine if KL is considered a tangent. For KL to be considered a tangent, the point of tangency needs to be perpendicular to the radius that connects to that point. So we need to check, does that make a right angle? To check that, we need to see, is this a right triangle? All right, so we're going to use the Pythagorean theorem. All right, we're going to use a squared plus b squared equals c squared. A would be one of the legs, so let's do 8 squared plus the other leg, 15 squared equals, and then we don't have the entire hypotenuse written. The part we're missing is from here to the center, which is a radius, so 8. So our hypotenuse is 9 plus 8 and quantity squared. So 8 squared is 64 plus 15 squared is 225 equals, and then 9 plus 8 is 17, so that's 17 squared. 64 plus 225 is 289. 17 squared is 289. So yes, those two are equal. The Pythagorean theorem holds, so we can say that yes, the line is tangent to the circle. All right, so I want you to pause here and try this next one on your own. Determine if HG is a tangent. All right, let's go through it. So we're checking to see if HG is perpendicular to the radius GF. So we're going to use the Pythagorean theorem. For our hypotenuse, this radius that we don't know is also 6. So our hypotenuse is 6 plus 12. And in the end, we get that the Pythagorean theorem does not hold. These are not equal. So then that means this is not a right angle. So no, the line is not tangent to the circle because it's not perpendicular to that radius. All right, moving on. Find the value of x given that BC is a tangent. So if BC is a tangent, that means that the radius AC is perpendicular to it. So this is a right angle. So it is a right triangle. And then we can find the value of x. So we use the Pythagorean theorem again and put in x for one of the legs. So x squared plus 14 squared equals, and we have the entire hypotenuse this time, so 17 squared. X squared is just x squared plus 196 for 14 squared equals 289. Subtract 196, get x squared is 93. So then x equals the square root of 93. We cannot reduce the radical, but if we were to round it to the nearest hundredth, we would get x is 9.64. All right, next one. Find the value of x given that JH is a tangent line. So since JH is tangent, that means the radius GJ is perpendicular to the tangent. So it's a right triangle, so let's use the Pythagorean theorem to solve for x. So leg squared, so x squared plus the other leg, 12 squared, equals the hypotenuse squared. We are not given the entire hypotenuse technically, right? It's not a single value, but we've got the radius x, and this length is 8, so the hypotenuse is x plus 8. So x plus 8 squared. So x squared plus 144 equals, to do x plus 8, the quantity squared, we need to do x plus 8 times x plus 8. So x squared plus 144 equals, and then we need to distribute, so x times x is x squared, x times 8 is plus 8x, and then 8 times x is plus 8x, 8 times 8 is 64, and then we can combine like terms. So we get x squared plus 144 equals x squared plus 16x plus 64. We have a single x squared on both sides, so if we subtract that from both sides, it cancels, and we have 144 equals 16x plus 64. And we can quite easily solve for x. Subtract 64 from both sides, 80 equals 16x, divide by 16, 5 equals x. All right, I want you to pause here and try this next one on your own. All right, the setup is pretty similar to that last one that we just did. We know one leg. We know that the hypotenuse is 2 plus x, or x plus 2. This leg here is just another radius. Like this is a radius here, so this is x. And then we set it up the same way as that last one and solve to get that x equals 3. All right, moving to the back. Common tangents. Common tangents are when two or more circles share a tangent line. So circle F and circle G have a common tangent of L. Then we have the common tangents theorem, which states that if two segments share a common exterior point, in this case B, so this segment shares this point, and this segment shares this point, and the segments are tangent to a circle, so AB is tangent with a tangent point of A, this one's got a tangent point of C, and then the segments are congruent. And then we have circumscribed polygons. So these are polygons created by common tangents all the way around a circle. So if we look at this triangle here, it's circumscribed. It's saying that this side of the triangle is tangent to the circle, this side of the triangle is tangent to the circle, and this side of the triangle is tangent to the circle. And then if we use the common tangents theorem, this segment and this segment are tangent, so these segments are congruent because they share an endpoint. These two segments share an endpoint on the outside, and they're tangent, so these are congruent. These segments share an endpoint, and they're tangent, so these are congruent to each other. And you're able to kind of figure some things out using that. All right, so let's go through some examples. For these first four, how many common tangents can be created by these different types of circle pairs? So this first one, common tangent, image we had a line going between the two circles. But if I draw the line that intersects here, that's not a tangent to either circle because it intersects it twice. It should only intersect one point on the edge of the circle. So I see a tangent, a common tangent here, where it's tangent to the circle here and here. And then I see one below the circles doing the same thing, tangent, tangent. And those are the only two tangents for this one, two common tangents. These two circles here, well, I see the same thing there where we've got one tangent, common tangent below, And there exists one above, tangent, tangent. But then I also think we've got two in between them, right? There's not just one in between, right? That doesn't touch either of them. But if I angle it, that would be tangent to both circles. And then if I do that again the other way, that is tangent to both circles. So these two circles have 4 common tangents. Next one. I can see again we have the tangents below the circles and the tangents above the circles. And then since the circles themselves are tangent to each other, they intersect at one point, then you can draw a line through that single point that is also tangent to both circles. So there are 3 common tangents. And then the last one. So these 2 circles are also tangent, but one is inside the other. So there's only one line of tangent line that these circles share. All right. These next 2, I want you to try these 2 on your own. So these 2 are using the common tangents theorem. So if 2 segments share a common exterior endpoint and they are tangent to a circle, then the segments are congruent. So if you look at both of these, you are told to find the value of x and the following segments are, if the following segments are tangent to the circle. So BC, AB and BC are tangent to the circle. They share the point B. So using the common tangents theorem, find the value of x. So same thing for the second one here. So pause here and try these 2 on your own. All right, so for the first one, since they are common tangents that share the same endpoint, these are congruent, so we set them equal, and we get that x equals 20. And then for this one, QS and RS, or not QS, how about this? RQ and RS are tangent to the circle. They share R, so these are congruent, meaning you set those equal and solve for x, so you get x equals 6. All right, last one, we've got some circumscribed polygons. A graphic designer is giving directions to create a larger version of the triangular logo shown. If triangle ABC is circumscribed about circle G, find the perimeter of ABC. So the fact that ABC is circumscribed about the circle, it means that side AB is tangent to the circle, BC is tangent to the circle, and CA is tangent to the circle. So we're going to use our common tangents theorem to find these missing side lengths so we can get the perimeter, so the length around the entire triangle. So let's start with A. That segment A, endpoint A, shares these 2 segments. So if AD is 8 feet, well then AE is congruent, it is also 8 feet. So then if we use the exterior point B, BE is 7, so that means BF is also 7. And we're told this entire side is 10. I think that's going to help us on this next part here, because for C, we don't know CD or CF. But since BF is 7, 10 minus 7 would be CF. So CF is 3, so CD is 3. So the perimeter would be AB plus BC plus CA. Well, AB is 8 plus 7, which is 15. We are told that this is 10, and 8 plus 3 is 11. So 11 feet plus 10 feet plus 15 feet, perimeter of 36 feet for triangle ABC. All right, moving on. Find the value of x if the perimeter of the circumscribed quadrilateral is 18 centimeters. Okay, so using what we know, let's start with T. Okay, it's a circumscribed quadrilateral, which means TU is tangent at B, UC or UR is tangent at C, RS is tangent at D, and ST is tangent at A. So since TA is x, that means TB is also x. Since UC is x, UB is also x. Since RD is 3, RC is also 3. And since SA is 3, then SD is also 3. So to write our equation, we know that the perimeter is 18. So if we add up all the sides, we get 18. So let's add up all the sides. So this side here is x plus x, so 2x. This side here is x plus 3. This side here is 3 plus 3, which is 6. And this side here is x plus x, which is, or x plus 3, which is x plus 3. So if we add this up, we have 2x plus x plus 3 plus x plus 3 plus 6 equals 18. We can combine some more like terms. So 2x plus x, that's 4x. 3 plus 3 plus 6 is 12. That equals 18. So if we subtract 12, we get 4x equals 6. Divide by 4, we get that x is 6 over 4. But that can be reduced to get x equals 3 over 2, which is also 1.5. So I'd accept either of those answers there. And that completes the notes for 10.5.